In this module, Module 3, we're going to talk about logic gates and noise margins. So we're going to come back to George Boole, who introduced Boolean variables, binary variables, and he also introduced the three fundamental logic operations, and, or, and not. So we're going to look at these in terms of logic gates today, and later we're going to look at them in terms of manipulation in equations. So logic gates perform these logic operations: inversion, not, and or, as well as NAND, NOR, and some other operations that we'll talk about. But they're all built on the fundamental operations of not, inversion, and or. So we have single input gates as well as two or multiple input gates. The two single input gates are NOT gates and buffers. We also have two input gates, which are AND, OR, XOR, NAND, NOR, and XNOR. And each of these two input gates can also be expanded into multiple input gates. So let's talk about each of these, starting with these single input gates. So the single input logic gates are the NOT gate, also called an inverter, and it has both the name and symbol. So the symbol is a triangle with a bubble. The bubble indicates inversion. And it has an input, or input A, on the left, and the output Y, on the right. So typically in digital logic, inputs start from the low end of the alphabet, A, B, C, D, E, and outputs from the higher end, W, X, Y, Z, etc. So we also have an equation, and this equation is read Y equals not A, or Y equals A bar. And finally, we have a truth table to indicate the function of the gate. So the truth table indicates the function of the gate. For every possible input, we want to know what the output will be. So that's one really nice thing about binary or digital designs, is that very limited number of possibilities. We're, again, using our digital discipline to limit the possibilities that we're going to consider. So A can either be 0 or 1. If A is 0, well, it inverts it, takes the inversion of that 0 and turns it into a 1 on the output. If the input, on the other hand, is 1, then the inverter will, or the NOT gate will again invert it and make it a 0. A buffer, on the other hand, again has the name, symbol, equation, and truth table, each of the parts to specify it, as in the inverter or the NOT gate. So the buffer's symbol is just a triangle, input A, output Y, and the equation is read Y equals A. And the truth table is expected, output Y. If the input is A, output Y is 0. Input is A is 1, output Y is 1. And so buffer takes whatever its input is and just delivers it directly to the output. You might ask, well, why do we have a buffer then? That seems kind of, why not just a wire? Well, buffers are useful in many ways. One of them is they provide delay if more delay is needed. The second one is that it can actually make a kind of not great input and turn it into a better input. So if you think of the like repeaters on power lines, they take a kind of not great input signal and boost it up so it's a better output signal. Okay, but at this level, this higher level of abstraction, what we need to think about is y equals a for a buffer. If the input is 0, output is 0. Input is 1, output is 1. So those are our two single input logic gates. And now let's talk about the two input logic gates as well. So we have an AND gate here on the left. So the symbol is a line with a rounded end on the output. So our AND gate, in this case we have two inputs, A and B, and the output is Y. This is read Y equals A and B. This is again the equation. So we have our name, symbol, equation, and truth table again. So the operator that we use looks like a multiplication symbol. So y equals A and B. But you'll notice that in this equation up here, the AND symbol was left out. So just like in multiplication, y equals 2x. Well, we could have said y equals 2 times x, but we often leave that out. It's the same with the AND operator in Boolean algebra. So y equals A and B. I can put the AND symbol in there, A and B, but I can also leave it out, as shown above. But either way, this is not read y equals A times B. A times is wrong. A times B. Nope. Okay, so this is read y equals A and B. And this operator, the AND operator, works as follows. Well, both conditions have to be true in order for the output to be true. So you could think of an example. You can go to the movie if you get a ride and you have the money to pay for the ticket. So both of those things have to be true in order for you to see the movie. If you have a ride, no money, not going to see the movie. If you have the money, no ride, not going to see the movie. No money, no ride, definitely not going to see the movie. So both conditions have to be true. Both A and B have to be true in order for the output to be true. So the only case where the output is true for this gate is in the case where A and B are both true or 1. Remember that 1, true, and high are interchangeable terms. Okay. So in every other case, the output is 0. Both of the inputs have to be true in order for the output to be high, to be true. An OR gate on the right here, the OR gate, again we have the name, symbol, equation, and truth table. The OR gate symbol has a rounded input followed by kind of pointed curve on the output end. So in this case, we have two inputs, A and B, and our output Y. And this equation is read Y equals A or B. So we adopt this or, this plus symbol to mean or. That equation is never read Y equals A plus B. Plus, It's not read. It's not read as plus. So y equals A or B, that plus is not optional. The plus symbol is not optional. It has to be there. So y equals A or B. Well, this is going to, the output y is going to be true if either A or B is true or both. So this would be the case of you can go to the movie if you have money or if your friend has money. So if you have money, great, you're going to the movie. If your friend has money, it seems like your friend's going to let you borrow some money, so you get to go as well. So either input being true makes the output true. So here's one of the inputs is true, B is true, B is 1. In this case, A is 1. In this case, both are true. Both you and your friend have money. Great, definitely going to the movies. So the only case it's not true is when neither of the inputs is true, or in other words, both of the inputs are 0. So the OR operation is true when any of the inputs are true. We also have other operations that are commonly used: the XOR gate, the NAND gate, the NOR, and the XNOR. So let's first look at the XOR, or that X stands for exclusive OR. It is not pronounced XOR. X stands for exclusive OR. In an exclusive OR, so the symbol looks like an OR gate, but has the extra line on the inputs. The XOR gate, with a symbol that is a plus sign with a circle around it. So the XOR, y equals A XOR B. The output y is true when either A or B is true, but not both. So it's similar to an OR gate in that it's true when A or B is true, but it's dissimilar to an XOR gate because it's not true when both of the inputs are true. So exclusive OR, the output is true when A or B is true, but not both. A NAND gate is, as you can see, it looks like an AND gate with a bubble on the output. This is shorthand for an AND gate with an inverter on its output. So it's a NAND stands for not AND. So NAND is a not AND gate. So the AND gate would have been true. Here's the AND gate would have been true here and only in that spot. So I'm going to write the AND function. A and B here would have been 0, 1, 1, 0, 0, 0, 1. So here's our AND function. And so it's the inverse of that. So we take wherever A and B would be true, well, NAND is not true. Whenever the A and B function, wherever the AND function was false, NAND will be true. So NAND is the opposite of AND. NOR, same thing, in that it's a OR gate, not OR, NOR. So we have our OR gate followed by an inverter, shorthand with that. That inverter is shortened to just a bubble. So OR would have been true, A or B, I'll write it just next to here, would have been true whenever either A or B or both are true. So not OR would be the opposite of that. We get 1, 0, 0, 0. So a NOR gate is a not OR gate. Now, XNOR would have been nicer if we could said not XOR. So if we could have called it a XOR, it's just too hard to say. That's really what it is. It's a not XOR gate. So it's the inverse. Here's our XOR gate. It's the inverse of that. Again, this inverter is shortened to just that bubble. So XNOR is the opposite of an XOR gate. So here we had 0, 1, 1, 0 as our outputs. Here we'll have 1, 0, 0, 1 as our outputs. So here, written nicely, we have our outputs for XOR. Output is true when A or B is true, but not both. NAND is the opposite of AND, so it's not AND. OR is the opposite of, NOR is the opposite of OR, not OR. And XNOR is the opposite of XOR. One other thing to note here is that XNOR is also known as the equality gate because it will output a true value when the inputs are equal. So both 0 or both 1. XOR is also sometimes referred to as the inequality gate. Its output will be true when the inputs are not equal. And will be false when they are equal. Okay, so let's look at multiple input gates. Here's a multiple input NOR gate. So a NOR 3, a 3-input NOR gate. So again, this is shorthand for this functionality, the inverse of an OR gate. So OR would have been A or B or C would have been true in all cases but the 0, 0, 0 case. So all of the other cases would have been 1. And sometimes in these tables I'll put a line here to keep alignment. So this one, the NOR gate is the opposite of that. It's only true in the 0, 0, 0 case. All other cases are false. Extrapolate from the 2-input NOR gate case. And 3, well, A and B and C, well, only going to be true if all of the inputs are true. You can go to the movies if you have a ride, you have the money, and you bring your little brother. Okay, all of those things have to be true in order for you to be able to go. So all of the inputs A, B, and C have to be true to make the output true. Otherwise, it's false. The output is false. We can just write those in again. Put that line there to keep alignment. So let's look at the XOR gate. With multiple input XOR, the output is odd parity. That is, the output is 1 when an odd number of inputs is 1. So here we have one of the inputs being 1, that's odd. 1 input is 1, and 3 inputs are 1. So we have 3 inputs being 1, and in these cases we have 1. So the output is 1 when an odd number of inputs is 1. This definition still holds true for the 2-input XOR gate too. So XNOR 3 on the other hand. So if we had XNOR 3, some output, say W, would be the opposite of this. 1, 0, 0, 1, 0, 1, 1, 0. So the XNOR gate for multiple inputs, the output is 1 when an even number of inputs is 1.